Hey, today I'm going to give a quick review of linear elastic fraction mechanics, also called LEFM. And linear elastic fraction mechanics is a topic that is taught in school. A lot of people have seen the theory for it. It's kind of an interesting theory by itself. And it's a good stepping stone to nonlinear or elastic plastic fraction mechanics, which is really more useful for polymers in general. But in order to get there, I like to talk today about linear elastic fraction mechanics, the basic type of fraction mechanics that one can apply. So let's start by talking about what requirements are in order to use LEFM. And the first one to realize is that this applies when the material is more or less linear elastic in its response. And that can happen for polymers in certain circumstances. If you have a very low temperature, for example, the response can be almost linear elastic, when the response, on the other hand, can be very different at elevated temperature, as we know. So this is not a material-specific property. It depends on temperature. Similarly, strain rate has an influence on the ductility and brittleness of polymers. At really high strain rates, the material can be more brittle, and then under those circumstances, linear elastic fraction mechanics may actually be more useful as well. So keep in mind, temperature and strain rate are properties or environments that influence if linear elastic fraction mechanics is suitable for a given polymer or not. The most basic theory for linear elastic fraction mechanics was originally developed by Griffith. And this was a long time ago, where he came up with this energy-based condition for when a crack will propagate. And this is really elegant and very simple. It's basically say that if a crack will propagate if the associated reduction in total strain energy, if the energy reduction in the strain energy is larger than the surface energy required to grow the crack. And that's written in mathematically here. So if the whole part reduces its total energy when the crack grows, then it will grow. And this works. And the problem, though, is that it requires that there is no dissipated mechanisms in the material. So practically speaking, if you want to apply this, it only works for very, very brittle material like glass, for example, not polymers, because close to the crack tip, there typically will be dissipated energy due to plasticity and other mechanisms. But if you don't have that, then the Griffith theory is just fine, and it actually works pretty well for glass-type materials. This was extended a bit by Irwin a little bit later, and he came up with an energy-based condition too. And he's using the idea that if you consider something called the potential energy in a part, and how the potential energy changes if a crack were to grow, and you form this quantity here to the right, where you see the W is the work done by external forces, U is the stored elastic energy. So this is the potential energy, the change in potential energy with crack size growth. And that is a quantity that he called the energy release rate. And the fracture condition simply is that if the energy release rate exceeds a critical value, Gc, then fracture will occur. So this is an extension that actually allows for some plasticity, a really close to crack tip, or any dissipated mechanism like that. As long as you have a field outside that region where the response is driven by linear elasticity. So this is kind of an interesting idea that he came up with. This is also a similar foundation to elastic plastic fraction mechanics that I will talk about in a different video. Let's say a few words now about types of fracture modes. There are three types of fracture modes one can come up with: mode 1, mode 2, and mode 3. One is an opening mode, and that's the most common mode in brittle fracture, which is linear elastic fraction mechanics. But you can see that in theory you can have these other modes as well. It's interesting, if you were to study fracture of brittle materials, in what direction will cracks start propagating? So here's an example. We have a specimen with a horizontal crack that's pulled in tension. If you pull more and more on it, at some point cracks will grow, and they will grow in this direction, perpendicular to the loading direction. That's pretty obvious. But what if the crack is initially vertical like this, and you pull on it more and more? What will happen to this crack? Well, there is no force to grow this crack, so it won't grow actually. It's pretty interesting. But what if the crack is at an angle like this, and you do tension on it? what will happen in that case in brittle linear elastic fraction mechanics? It will grow wings like this, as you can see, and they will grow in the perpendicular direction to the loading direction. And here's the last one that I think is interesting. If you do compression instead, so if you 45-degree or some angle to this initial crack, and you do compression on it, what will happen to this crack if you keep loading it? It will go cracks in this direction, actually. It will be causing, these are called wing cracks as well. So you can get crack growth in the uniaxial compression if you have cracks that are oriented at an angle to the load direction. So that's also kind of good to have some intuition about. What Irwin talked about too when he derived fraction mechanics back in the day, he started to looking at stress fields around crack tips. So here's a situation where we have a horizontal crack and we have a uniaxial tension far field. And we're looking at the coordinate system that's specified by r and theta. And we want to figure out what is the stress at any point surrounding the crack tip. And if you do some fancy math and you assume the material is linear elastic, you can actually calculate closed form equations for what the stress will be. The stress in this case is 3 stress components. It's a 2D problem, so sigma xx, yy, and xy, and they're given by these equations. It's pretty interesting that you can actually perform this calculation. That's something that people back in the day did a lot of work on, because computers weren't invented really back then. So they were very smart and they came up with these equations for how the stress depends on the angle and also the distance from the tip. And as you notice here, the stress itself is proportional to 1 over square root of r. So if r goes to 0, the stress will go to infinity. And this is truly what happens in a linear elastic material model. In real life, of course, stresses can't go to infinity. But we also see an interesting thing here is that the strength of this stress field is dependent on r and theta, but also on a constant k1 in this case, in mode 1. So k1 is the strength of the stress field. And let's look a little bit about the stresses in the plane that's directly in front of the crack. So in the plane, theta is equal to 0. We just put that into the equation on the previous page. We'll see that the opening stress, sigma yy here, is equal to k1 divided by square root 2 pi r. And clearly, this is a stress that will start at infinity and then decay as r increases. What's interesting here is to consider the situation where this opening stress reaches the yield stress of a material. So now if we're talking about the real material that has some yield stress, if we replace the sigma y, the opening stress, by the yield stress, we can solve for the r. That would be the distance from the tip where the stress will reach the yield stress. So that will be the plastic zone size. So that's how big region in front of the crack tip that you will actually have stresses that exceeds the yield stress. And the point here is that outside that region, outside the plastic zone, you will have a stress field that is given by the linear elastic stress response. And that's why linear elastic fraction mechanics works under those circumstances. So another way to specify a fraction mechanics condition for linear LEFM is to use this stress intensity factor K1. So K1, as we talked about, is equal to a geometric constant times the far field stress times square root pi times the crack size, the initial crack size. And failure occurs if K1 is exceeding the K1C, the critical value of K1. This requires initial defect. And this equation here, the A parameter here, the geometric factor, depends on what type of crack it is, what angle it has, how many other cracks are in the neighborhood of this crack, etc. And there are some interesting books. I happen to have this book, the Stress Analysis of Cracks Handbook. It's a thick handbook, the page after page of different configurations of cracks, and it tells you what the stress intensity factor K1 is for all of these different configurations. And that can be kind of interesting and useful sometimes. Finally, also note that the energy release rate, G1C, can be related to the K1C value in this way. And I'm not going to show that or prove that here, but it's a relationship between them. Instead, I want to say a few words about experimentally measuring the K1C value, so the critical value. And there is ASTM standards for doing that. This is a compact tension specimen that some people have seen perhaps. It's a very specific specimen geometry that you put in a test machine, you basically rip it apart, and you measure the force as a function of displacement as you rip it apart. In order for this to give you a good stress intensity factor, critical stress intensity factor, the standard says that this condition needs to be satisfied. So what this means is that all dimensions of this specimen needs to exceed about 15 times the plastic zone size. That's really what it comes down to. So that means that when you test it, you don't want to have a plastic zone in front of this crack tip that is close to the size of the specimen, because then you don't really measure the K1C value that's required for linear elastic fraction mechanics. And so that's something to keep in mind. The problem, though, for some ductile polymers like HDPE, the size of the plastic zone it can be very large. So you can't practically perform these experiments where you actually measure K1C for those materials. And that is another example of why you need to switch over to elastic plastic fraction mechanics, because that's another test that can be done and that's easier to perform. So here is just a picture from the ASTM standard that shows you do some measurements and then you do some construction on the force displacement graph, and that gives you the critical stress intensity factor experimentally. You can also perform finite element simulations of different crack geometries and determine the K1 value for a given crack that you're interested in. So I talked earlier about the handbook that has numbers and values and tables for that, but you can also do it in finite element simulations these days. There are two basic ideas for doing this. One is to do a sharp crack and one is to do a blunt crack. If you do a sharp crack, you need to actually be very careful what type of elements you use and where you put the nodes in these elements. The idea here is that you want to have a specific configuration such that you get an infinite stress, and you get a stress that depends on the distance from the crack tip with 1 over square root r. And you can actually achieve that by having quarter node positions and this and that. I'm not going to go into it here, but it's available in finite element programs to calculate the stress intensity factors for various cracks in this way. Again, as I said at the beginning, most of the time I wouldn't do this because I would not use linear elastic fraction mechanics. I would use elastic plastic fraction mechanics, which is more suitable for thermoplastics and other polymers. But it's available if you want to use it. So to summarize, linear elastic fraction mechanics is well known. A lot of people have studied it in school. It's kind of a fun theory, but in real life, it's not that useful. I don't see a lot of people actually using it. And that's why elastic plastic fraction mechanics is a more suitable topic in many cases, and I will cover that in a separate video.